I'm not.
Okay.
Cool.
Okay, very good. Welcome everybody. Thank you very much for coming along to the latest Shocklab seminar. We are extremely happy to have Naoya here from electrical engineering. We're particularly happy when we have people from other departments and even other faculties here to talk with us. Naoya is working with Amir Patel on the motion capture systems for wildlife.
Thank you. Hi, I'm Naoya Muramatsu. Today I will show you my PhD research, what I've done and what we do next. And my research project title is the motion capture system for the wildlife, and my supervisor is Dr. Amir Patel. So before diving into the PhD topic, I will introduce about myself. I'm from Japan, and I took my master's degree in University of Tsukuba in Japan, and I've developed many robots. Okay. These pictures are some of my robots I've made. I made the hardware too, but my main interests are the software and its algorithms. So my current research works are deeply related with machine learning and computer vision. About the industrial experience since an undergrad student, I've been working in some companies. Now I'm a PhD student, but I also I have my own company and supporting some tech companies like, how can I say, technical consulting or something like that. So my job title is CEO, but the working style is like a more freelance. So So I know your question, why did you come here? So many people are asking, why did you come to South Africa or UCT? So the answer is very simple. I'm interested in robotics and animals, especially cheetah. My ultimate goal is to develop a robot moving like animal, like a beautiful animal motion. And then I was looking for professors and laboratories all over the world. And I also checked many countries, not only US and Europe, but also some India, China, or any other small countries. And I found Dr. Amir Patel. So actually he's a kind of a famous professor for cheetah and robotics research. So as I said, he's my current supervisor. His research purpose is super same with mine. So he was here, so I was here. Okay, so Amir and I are interested in the beauty of animal motion or locomotion. Specifically, how does the cheetah control its body, and can we reproduce the motion with a robot or robots? These questions are too big for one PhD student, so I broke down it. So now I'm focusing on the observation phase for the bio-inspired robotics. My key question is, how do we analyze the motion in the wild? So in the wild, not in the laboratory. So like many works is observe the animals or like pet-like animals in laboratory settings or fancy 3D scanner in the world system. And then I checked many sensor systems. I will show you the details later, but the conclusion is there is no proper sensing system for wildlife. So I developed some sensor systems and the algorithms that I will show you soon. So thank you for your patience to my long introduction. In the following slides, I will introduce you first the existing animal observation tools or methods, and then I will explain my research journey, including fieldworks. This is a quite long presentation. I don't know, it's a 50 minutes or something. Please ask me just when you come up with a question. You don't need to wait at the end of my presentation. Okay, let's start the literature review first.
I have a question.
Okay.
Are these your photographs?
Okay. Here.
Oh, no, I mean the ones of the cheetah.
Oh, okay, okay. No, no. It's this is a kind of, how can I say, online cheater pictures. But I will show some my own pictures later. Yeah. So I will summarize the works of cheetah kinematics. So x-axis shows the complexity of cheetah model, and y-axis shows whether the subjects are captive or wild. The left bottom area indicates the traditional animal locomotion studies, tracking the cheetah's leg motion by human eyes and analyzing the locomotion. So Dr. Wilson's team in UK, it's a very famous professor team, is focusing on the left top area. They use self-developed GPS IMU modules. This device can easily observe the wild cheetah's movement in the first area. For example, here he researched the interaction between predators and prey using a lot of GPS IMU modules in the wild situation. Yeah. So yeah, but however, each subject is analyzed as a single point or simple point because the device it's just put on behind the neck or just put one or two positions of animals. On the other hand, our previous works and a few others have been focused on the right bottom area. We've made a skeletal model with a multi-camera system and trajectory optimization. So as you see, now I will tackle to the top right area using the novel algorithms and sensor fusion systems. So another important aspect for animal research is invasiveness. In an ideal case, we can put many metallic sensors on wildlife's skins or under the skin, but however, that's impossible ethically and financially. In the plot, the y-axis shows the invasiveness for data collection. The above is more invasive. Technically, we might be able to put some sensors inside the animal, so like I said, such like a microchips or something. But fortunately or unfortunately, I've never seen the kind of works. So many people use GPS IMU modules, self-developed or off-the-shelf ones. X-axis shows the number of key points or observable points on one animal. Some researchers put the phosphorate, so there, phosphorate under the ground of national parks. So it's very how can I say, manual-based approach. And we are developing systems to record animal locomotion using the multiple cameras or some remote sensing systems. So, we can completely remotely observe the animal motion and high resolution. Yeah. So my research objectives are capturing data of high-speed animals in the wild, and we are engineered so to use the data for engineering applications like robot controls. We need to collect the 3D motion data. The kind of system is a key tool for robotic robotics, and biomechanics. Okay, then the first work I've done is AsinoSet. This is a novel 3D motion data of cheetahs. So this research collaborated. For this research we collaborate with the Amban Deep Cheetah Center. They helped a lot us. So AsinoSet provides the 3D motion reconstructed with full trajectory estimation, or FTE. So we observe the cheetah running or walking with 6 cameras and point out the key point on the 2D markers pose estimation. So deep report is a kind of popular tool for this kind of research. And then, just how can I say, estimate the 3D points using triangulation. It's very noisy, so we use we assume some cheetah kinematics model, then optimize the trajectory use full trajectory estimation approach. So this is a result motion. So okay, so the idea is very simple, but we made some technical problems. So the first problem is occlusion. So occlusion refers to the situation where the target is particularly or fully blocked from views by another object. So even with the 6 camera systems, the occlusion could not be avoided. Especially in our case, cheetahs were running outside. So dust often covers the poles, and the lack of some key points leads to collapse the estimated body pose in the model-based approaches. So we modeling the rigid bodies. So if some key points weird, the whole estimated body looks weird. So then we introduce a pairwise pseudo measurement. Okay. Okay, we cannot say okay. Okay, so in this scene, so the right hind beam pole is occluded by dust. So this is the angle, and here is the pole, but you cannot see the pole, right? But using neural networks can be trained to estimate the relative position vector from other key points. For example, in this case, we can guess the pole position using ankle and knee. These vectors are called pairwise term. And these vectors are considered in the full trajectory estimation, like this workflow. In the FTE process, the 3D pose is estimated from the 2D key point and the pairwise stance. So we evaluated this approach by ablation experiments. The burst value shows the dropout. The number of dropout samples. As a result, pairwise FTE, PWFTE, reduces the reprojection error by a factor of 5. So the second problem is shutter delay.
So can I just ask, can you get back here? So is it possible to take measurements where there's no occlusion and do a masking and train on that data to improve these sorts of measurements? So actually train on taking away measurements.
Yes. So without pairwise term, we need to estimate the 3D posts without the pole position.
Yeah.
But using the pairwise term, we can how can I say it? Assume or appropriate 2D positions from each views.
But I mean, when you're doing the training,
Mhm.
you need a ground truth. So
Yeah.
what's the label that you use when you're doing the training of the neural?
Oh, I just so okay, so
Is it from a masking?
yeah, just masking. So
Oh,
yeah, even it's visible, but we just
right,
consider that.
no, that was okay.
Yeah. All right. So yeah, the next trouble we met is a shuttle delay. So the reconstructed data of a sunset are better than the traditional reconstruction methods. So using triangulation. Nevertheless, the accuracy is not enough for small pose estimation, such as head direction. Yeah, this is a reprojected 3D position of from estimated kinematic model, but the eyes and nose position slightly different, right? And yeah, because the cheetah running at the 12 meters per second moves 10 centimeter in a frame, even with 120 FPS cameras. So we use the GoPro, so the FPS is quite high compared to other cameras. For this reason, I had to estimate the state between frames because we cannot wholly synchronize the shutter times for 6 cameras. So inspired by Professor Bourget's work, I implemented the algorithm considering the shutter delay parameters tau I for each camera and optimized them simultaneously with other parameters of the FTE. So we assume between the shutter delay, the target object moves some constant velocity or first or second order approximation motion. So this is a result video. As you can see, it's very difficult to see. Yeah. Okay. Here. So this is a traditional FT result. So the reprojected 3D points is slightly different from the original position, but considering the shutter delay, we can perfectly match the 3D points and to the key points. So yeah, this is a quantitative result. Then this is a reprojection. Y-axis shows the reprojection error. So blue bar shows the FTE result, usual FTE result. The red and yellow bars show shutter delay FTE results. The two types of shutter delay FTEs are defined for the approximation order. The red one is considering first order approximation, and yellow is the second order approximation. So velocity, considering only velocity for the red one, and yellow one considering the acceleration as well. And yeah, so as a result, shutter delay FTE decreased 31% of reprojection error. And there is no big difference for the first and second order approximation. So yeah, so our conclusion, we should use first order approximation for our data. Yeah, then we combine the two methods to improve the usual FTE. So pairwise shutter delay FTE. This is our final workflow. So after the 2D key point detection and the pairwise pseudo measurement, shutter delay FTE reconstructs a high accurate 3D trajectory. And this system can resolve the occlusion and shutter delay problems. Yeah. So this video shows the qualitative results. So using the usual FTE, the especially complex pose is very difficult to reconstruct, but using shutter delay and pairwise, we can reconstruct proper, how can I say that, leg poses.
Can I just ask, so I guess it's independent of the shutter delay aspect. But you're doing this essentially on a frame by frame basis?
Yeah, so for example, camera one and camera, in this case, camera one, camera two, right? So camera one getting the images 120 fps, also camera two equals 1 fps, but that's, how can I say, shutting times is not completely matched.
Sure.
So slightly different, right? So this different gets a big error for high speed motion.
But in the sense that if you've got for one frame, you've got your predicted position, you've got your sort of your skeleton, and you have the velocity. You can have a prior on where you expect it to be in the next one. Can you utilize that also? You can utilize the prior information.
Yeah, yes. So yeah, if we think the camera one is the baseline for every camera, so then we slightly adjust the 2D key point position based on the tau 2 in this case. So tau shows the shutter delay. Yeah. Okay, so yeah. And so yeah, recap the algorithm. So we proposed two methods to solve the occlusion and shutter delay problems for high-speed multi-camera systems. Then pairwise shutter delay FDE achieved a better result in the cheetah motion dataset. This approach is not reconstructed in cheetah scene. We can use the method for other high-speed object capturing system application. That's my first work as a PhD student. So yeah, the next topic, my topic is wild pose, long-range motion capture system. This work is supported from Google, Microsoft, and we collaborated with Oxford University for data analysis. So first, I will explain the program settings for wildlife observation. So in the astroset work, we observe the cheetahs outside of the lab, but the cheetah are tamed or very human friendly. So, but real life, no. They are timid, not only about the herbivores, but also the predators. I never seen lions very aggressive to humans, like in the Hollywood movies. And from the ethical side, we should not affect animals' behavior in natural settings. Thus, the researchers should observe them at a long distance. So there are several options for the data collection, but we require three features for the system here. So availability outside, portability, and the capability of 3D whole body data collection. So the demand for 3D data is increased in recent years, so which must be the requirement for the next generation system. And yeah, so many researchers have developed 3D capture systems like multi-camera systems like astroset, or we can use traditional mocap-based markers. However, these are not portable and not suited for outdoor environment, especially under the strong sunlight, because they heavily rely on IR light. Camera trap system is available to record animals' 3D whole body data by using depth camera or multi-camera system like multi-camera system, but still not portable. So GPS IML color is, as I said, is popular tool for wildlife research, but the data resolution is very limited. Photography is also popular and easy to use for everyone, but it cannot provide the depth of information. So this is one of my favorite approach as a related work. Zoom lens stereo vision is a new approach. So they put a set of mirrors and in the front of zoom camera to get the stereo vision from single image. The idea is wonderful to capture 3D dense information at the distance, but to make the long baseline between this M1s, the system is too big to work in national parks. Now we propose a novel approach for wildlife data collection to fit these three requirements.
Can I just ask with the drone, if you have multiple drones, can you not get 3D data?
I never seen multiple drone capture the wildlife of the wildlife locomotion, but I only see the one drone capture the giraffes walking data. They also get the 3D data from the known, how can I say, field lengths, for example, the waterfalls or something. But yeah, this accuracy is not so good, so we cannot reconstruct 3D whole body. So our key idea is to combining zoom lens camera and LiDAR. LiDAR stands for light detection and ranging. So yeah, simply it's a laser-based 3D scan system. We call this system Wild Pulse. So Wild Pulse has three key features: 3D data acquisition, portability, and long-range capability. So thanks to the LiDAR technology, the system can acquire 3D information with high resolution video. And the size of the system is small enough to carry during field work. Lastly, with Wild Pulse, we can collect the animal data even at a long distance. So we use a solid-state LiDAR, which scans the depth information only in the front side, but provides a denser points than usual LiDAR. So usual LiDAR used in autonomous vehicles or something, they scan every 360 degrees environment. The camera's zoom lens are controlled by DC motors. All the sensors are mounted on the active stabilizer for reliable wildlife observation in natural settings. The diagram shows hardware connection. So the control modules on this right side, controls the actuators and saves the sensor data. And the sensor modules left side puts the outside of a car during the field work. So we put this side inside the car and this side outside the car. And I control the systems using a gamepad controller and check the view using a portable monitor. So we pre-tested the system in the Cheetah Center. This is recorded data by Wild Pulse. So left side is a 2D video and the right side is 3D point cloud data by LiDAR. It's very difficult to see, but you can, yeah, these are trees or three. Yeah, here is this is a cheetah points. Yeah. But we, yeah. So yeah, we can get the high resolution 3D cheetah motion. So I will compare depth ranges with other products used in previous works. So in the real sense, would be the most popular one. Some researchers have used it for camera trap system. However, the maximum available depth is only 6 meters, which is too short to shoot animals with photographer style. A few latest products like Stereolabs ZX is better than the real sense, but the maximum range is still 20 meters. So wild boars can get the video and 3D information from 120 meters away. So we evaluated the measurement precision with a calibration board. Even over the 120 meters, the absolute error is under the 2 centimeters. So actually, this calibration board put the 120 meters away. But we are using zoom lens, so field of view is very narrow. So that's one of disadvantages for wild boars. So now I will quickly introduce some technical issues for the LiDAR and zoom lens camera system. We made 2 technical blockages, high throughput data and LiDAR cameras calibration. First, we need to record 170 FPS high resolution video and 10 FPS dense point cloud at the same time quickly, which is difficult even with the latest mini computer. To solve this problem, we replaced the default OS middleware to eCal. So eCal is designed for fast data transfer and record, but consumes a lot of storage during the sensing. The LiDAR and zoom camera calibration has not been completely solved. Especially, we need to treat the intrinsic camera parameters changing from scene to scene because they're using zoom lens. So we are now using a semi-automatic approach, which is based on the depth information of the LiDAR and the depth map estimated from RGB image, and try to match the both depth information automatically. But that's not perfect for the very small areas. But these small areas very important for zooming for far away. So yeah, so after the how can I say matching, I manually adjust the calibration camera parameters. Okay, so we made the nice system. So let's go to the fieldwork. So to collect the data, so Mike and I went to the national park, Kgalagadi Transfrontier Park. So here's Mike, it's me, and she's a ranger in the national park. So we put the camera sensor systems on the outside of the car, and yeah, this is a car door, and put the mounters and put everything on the mounter. It's quite heavy system. I think it's 7 kilograms totally. And yeah, you look at this picture is very beautiful, right? But inside is more messy. So to protect the sunlight and dust, I put every computer modules inside of the car. And I know I made a lot of robots, so I understand that I cannot completely every system completely at once. So we made the, how can I say, draft version of the circuit boards. So yeah, that's why the inside is super messy. So anyway, so this is a scene during the field work, and here a male lion sleeping under a tree. So this is a male lion, this is our system. Yeah, I think the distance almost 20 meters. So we also record the various animal data in the field. So cheetah PCZ, PCZ stands for pale chanting goshawk. It's a very popular hawk in Cape Town. and gamesbok and lion. I also observe other animals such as springboks or anything else. One of my favorite is the martial eagle. So to explain the uniqueness of wildlife data collection, I will show one video. So I recorded this video with iPhones. Okay. Yeah, iPhone 13 Pro Max. And actually, there is a, actually, you don't see that, but there is a giraffe over there. Okay. Yeah. Actually, there's a giraffe over there. And yeah, and the look is very small for iPhone camera, but clearly seen the with the zoom lens camera or wild pose. So now maybe you can understand why long range data collection is crucial for wildlife observation. Yeah, giraffes to the distance almost 90 meters based according to the LiDAR data. So I will show you one episode during the fieldwork. Actually, that's not related with my research, but it's my favorite and very impressive for me. So there's a cheetah family over from left side here, and springboks are resting there. So the distance might be, I think, 100 meters, and this camera shows our position. So this is low. We put the car here, and oh, there's cheetahs and there's a springboks, but very small. So, but because of the wind and springbok smell, maybe the cheetah would notice the springbok from far away. After that, then the mother star shows the mother cheetah leaves her children there and goes around. Actually, there's a hill, so behind the deer, something like that. So yeah, then she starts to hunt. Of course, the springbok is trying to running away, but yeah, it was pinned down by remaining children. So this is a video. Sorry for our bad skills for photography. It's quite difficult for super high-speed animals. Okay, yeah. Yeah, the mother is catch the springbok and children came here. Yeah, so yeah, this is a video and this is a 3D plot data during the for this scene. So it's quite hard to see the low point cloud data, but yeah, here's a cheetah and springbok, and oh yeah, another cheetah comes. Yeah.
So can I ask just in terms of the tracking, are you having to do this all manually?
Oh, manually, yes.
Is that something, would you want to do that automatically or?
Yeah, we also consider the automatic track, but it's super difficult to control, especially to control and for algorithms, because first the rig is very heavy, so to control the heavy objects is we need to prepare big motors.
So can't it be done with mirrors?
Yeah, that's another approach. I'm thinking that, but I'm not sure it's appropriate or not. And to control the zoom view using the remote system, it's super difficult. So we need to how can I say, like a target by gun. So you cannot if if you look at this side and control the gun, something like that, it's remotely, it's very difficult, right?
Yeah.
So, and yeah, so that's another reason. So that's why I'm thinking photographer style is yeah, good. And this thing is very special for during field work. 99% animals just standing, not so active. So yeah, yes. So and this is the overview of the drama. When I live in Japan, I didn't believe that these animals are so smart. Of course, I have watched some documentaries or seen real animals in a zoo, but I thought I know some these stories explained in the documentaries, but I thought these stories are exaggerated by filmmakers. But yeah, now I could understand it's real at the moment. Yeah, so that's not happened in a short time. It shows just I explained in 10 seconds, but it take at least 30 minutes after the leaving the mother or start hunting. So the cheetah obviously have the ability to consider long-term strategy for hunting. Okay, so back to my research story. So for the fieldwork, our sensor fusion system might be great, but how is it useful? So I will show some applications. So do you remember the giraffe video? For the same scene, we reconstructed the 3D body from wild pose data and measured some important body part lengths. We marked some key points on the 2D image frame, then project the 2D image to the 3D points. For example, the measured height is 5.5 meters. It's matched with other observation reports of African giraffes. Even though the data reconstructed from do you remember it's observed 90 meters away actually, but the measured lengths are more precise than the other methods such as photogrammetry. Actually, traditional biologists measure the how do you measure the wildlife giraffe's height? It's it's very I'm not sure. There's some approach. First, we just project some parallel laser on the giraffe body. Then, based on the parallel laser points, they measure the estimated height. Or, yeah, so they just guess, almost guess for other engineers. But yeah, we can quite accurately measure the wildlife body size. We also measure some Marshall eagles. Marshall eagles not so big like a giraffe. Almost, how can I say that? The width almost 1 meter, but very small. And you know, the bird is very sensitive for human motions, so we need to observe from long distance. So the next thing is this. So a male lion stands up and starts to walk. Actually, this lion is just sleeping there, and yeah, there was no shading here, so he just started walking. Just on this reason, there's no special reason for walking. This is the reconstructed data in 3D. So yeah, this is a video, and this is 3D data, 3D point cloud, hard 3D point cloud. This is the reprojected 3D points. So we can get the 3D pose motion from the scene. After the calibration, we reconstructed the scene and marked the 2D key point on the image frames. Then the 3D poses can be obtained. The key points shown by red. I labeled eyes, nose, and joints. And the blue lines are just connecting the key points. So by using wild pose, we could get 3D poses from data of a single viewpoint. As you see, the occlusion is the problem again, and some occluded key points cannot be detected, which is a limit of our current system. But we can use some model-based approach to estimate occluded body parts. So next, we observe the springbok group, and one of the interesting things is they are sparring here. Actually, sorry, it's a jittering video. Yeah. Yes, they're sparring here. And after the fighting, they just leave away. So by using a deep learning approach, we can track each individuals. Moreover, we could get the 3D positions. The vertical axis shows the time. So this is a spot. These are sparred springboks. So first, their distance is very close, but after the fighting, one of them lives there. After that, the other one lives there. But the whole group going to the goes left side of the view. So I've checked the precision with stationary individuals. So for example, these guys is almost just stands for a short time. So, and the error is only 4 centimeters, even where we recorded the data from actually these guys are 140 meters away. So that's why the video is so jittering. So next, in this scene, the female lion lay down on the ground and starts sleeping. So what we can do? So we could get the respiration pattern from the 3D shape deformation from 30 meters away. So we get the 3D map on this lion. Then we just measure the chest height difference. Difference. And yeah, actually, there's some tricks because the raw data is very noisy. So I apply some filtering process, but this filtering process is very common approach for other approach like video-based respiration pattern extraction. So if we evaluated the data with manual labels. So I manually click them. Labels. So the red area shows the inhalation and the blue shows the exhalation. So these are matched with the extracted patterns. So yeah, as I said, some researchers have proposed the methods to get the breath patterns only from video data or video data or some of video data. But compared with these vision-based methods, one of the advantages of our method is to get the relative magnitude in the pattern. For example, 4 to 6 seconds, the lion's breath looks like shallow and quick, which can be numerically shown in the extracted patterns. So again, here. So it's difficult to see, but first, slightly it's slow, but it's fast. But now calm down. It's difficult to see, but we can get we can extract this pattern from the numerically by numerically. So lastly, I will talk about the 3D mesh recovery from limited data. the problem is 2D to 3D mesh. So SML is not our work. SML is the most famous approach where optimizer estimates the 3D mesh only from a single image and joins with prior knowledge. So they so in this case, the prior knowledge is a 3D animal mesh mesh model represented by the low dimensional vector. This prior knowledge covers all kinds of quadrupeds, officially said. But this approach is not perfect. And for example, the prior knowledge is not completely, actually, this is not our data. This data from the animal 3D data set, but reconstructed pose is slightly different, but they said it's a ground truth. And yeah, this face looks like a female lion for me, at least. And yeah, because they made the kind of template data based on the animal toy. They scanned animal toys, then they how can I say, compress the complex mesh in low dimension. So yeah, that's one of the limitation. And they are computer vision scientists, so they try to optimize a good-looking shape, not a matrix size or something like that. So yeah, looks good is it's their goal. So it's not good for us. So we are trying to make the matrix accurate 3D mesh with the LiDAR data and some computational tricks, but it's under development. So the main idea is just input the image and depth information such as LiDAR or real sense, then reconstruct the matrically accurate data. So yeah, but still development. So sometimes the face is weird or something. And so this is our test scenes, and this is a 3D scenes. So this mesh is a estimated mesh. Yeah, there is some point cloud here. Okay, so yeah, something like that. So this shows the optimization process, and there's two images. This is the initial state, and this shows the final state. So we start the very random initial animal mesh. Then after the optimization, looks good, but based on the image and LiDAR data, and the shape is not super perfect. So we are trying to improve that. Okay, so let's recap my works. So you remember this slide. So I showed this part in my first part of my presentation. For each objective, I proposed some solutions. So first, we proposed a multi-camera system for high-speed objects. Then developed a long-range motion capture system for wildlife. Now I'm developing algorithms to recover complete 3D mesh from these data. Through these methods, I like to construct the animal motion data for robot locomotion. Lastly, I'd like you to bring these lessons. I know some quite long lessons. The first is South Africa is in a unique position. So as I came here, and we can easily access to the national parks and interact with cheetahs. It's very, how can I say, very unique, even for not only for Japanese, but also for US and Europe. And the second, you can not apply the standard method to extreme cases. I couldn't use a popular standard multi-camera system for high-speed animals. Third, the sensor system is key to record useful data. Recently, some many great computer vision research have been published, but the accuracy is not it's still not applicable for biomechanics or robotics application. Actually, some papers argue that. So yeah, the first, the prior knowledge is key to understand the world from limited data. So we cannot record perfect data with any sensors. The prior knowledge, like SML model, helps to interpolate the lack of data. The fifth, the data is key to make the prior knowledge. If we don't have the prior knowledge, we cannot reconstruct accurate scene. And field 6, yeah, fieldwork is very fun, actually. So if you have a chance, please join the research trip, or let's try to apply these positions. So you can get many ideas during the fieldwork. I'm not sure what you can get exactly, but I can guarantee you can find something. Okay, that's all. Thank you for listening.
Wonderful. Thank you so much for a really fascinating talk.
Yeah, thank you.
I seem to say this again and again with the seminars that we have, that it's lovely to have something which is completely different from anything we've heard before, and is fascinating. Yeah, are there any questions?
Yeah, I have a question. You said data collection is obviously very important. And you developed a system for sort of a lower cost data collection system. What would you say if you had unlimited budget for collecting the sort of data that would be useful for your algorithms? What would you need to capture, and how far is that from what we currently have?
Yeah, it's a good question. Actually, many computer vision team is trying to that. Some computer vision people, it's a 3D scan real holes, many horses. So it's quite expensive approach, but we cannot this approach for cheaters. So actually, I'm not sure. I will make some arena for cheaters, then scan the cheater data. We cannot completely tame the cheaters like holes. So we just observe the cheater with the complete data for a long time, then make some cheetah template model, so cheetah prior knowledge. Then we can apply the model for the wildlife cheetahs or other animals.
So do you think you could maybe reduce the costs further of the current system based on having very good priors with more expensive collection?
Yeah.
Trade-off there.
Yes. So that's why many researchers use the animal toy for prior knowledge.
Thank you. My question is, when you're collecting the cheetah data, was it only one cheetah you focus on, or there are several cheetahs?
Basically, we like cheetah. We like a fast, cool motion. So maybe that's a primitive reason Amir and I focusing on cheetah. But in my case, I made the wild pose system, so I can observe any kind of animals in the field. So yeah, but the interesting thing is for the cheetah as a subject, it's a very high speed, and their motion is very flexible compared to other animals. Yeah, so yeah, if we can solve the extreme case, we can apply the same approach to other animals, right? So yeah, that's why that's the official reason why we focus on cheetah. But the primitive reason, just a code.
So the initial sort of motivation for this was because you were interested in the robotic side.
Yeah.
So do you see a pathway from this data to take you to where you really want to be in terms of developing robots that have
actually, to be honest, I'm not sure the mechanical things for robots, but now I and some researchers is focusing on the reproduce animal motion to the robots. So yeah, some researchers try to do that, and so I'm quite sure we can apply animal motion to the robots, legged robots nowadays. Yeah, so but I'm not sure how to expand the mechanical limitation using animal data, but I believe it should be useful.
Yeah, the question related also to the data collection. So with the various cheaters, so how did the environment impact the data collection? So if it was really sunny, if it was rainy, if it was really cloudy or dark, was there basically the data annotation or data scrubbing you had to do in order to make it worthwhile?
Actually, at least for wild boar things, the weather is not so important. And I'm sure that the extreme case, but because the Kalahari basically sunny.
Yeah.
Yeah, very clear weather. So I never check the weather or snow condition like my home country.
Yeah, so that was my question. So if you have to transpose this method to other climates, how would it function?
I think I heard the LiDAR is very big for rain because water drop reflect later. So it's in this case the data is very noisy. But I think the more important things, at least our case, it's the environment because some you can see them. Yeah, for example, there's long grasses there. So long grasses broke the LiDAR laser. So we cannot get the detailed whole shape from the long range. So yeah, I think this kind of natural settings is more difficult question, difficult things for that.
Do you have any questions on the robotics?
Yeah, so I mean, you pointed out so with the mechanical mechatronics perspective, it's rather limited. So is there a path you can see like with soft robotics where you have actually actuated your synthetic muscles and things like that?
Yeah, it's a good question.
Inform such design.
I'm not sure. I feel some potential for the soft robotics and a lot of my not a lot of, but some of my Japanese friends is focusing on the kind of research. But currently, electric motor is more useful. DD motor is more useful, I think. Especially for the extreme motions. So other student of me focusing on some acceleration or deceleration of the not quadruped, it's by Peter, yes, sorry. Now we cannot directly apply the soft robotics actuators, but in the future maybe we can, but I'm not sure.
Right. So is there, so with our current approaches of electrical motors and actuators, there's surely an upper limit of like the speed they could reach. They could never reach this cheetah speed of about 110 kilometers
rather than speed
per hour, right? Yeah,
rather than speed, I think the for example, so flexiveness is more limited for the electric motor approach because we cannot make how can I say the cheetah running looks like more soft.
Yeah,
it's difficult to say, but I feel motion. That's not my specialty, so I'm not sure. But the motion principle it's slightly different from the mechanical motors. So yeah, I think that. But of course, the electric motor is very powerful based on the numerical data. So. Power is no problem, I think, but control or flexible or things, or it's more important things to mimic the animal motion.
So tell me, what is your next step? I think I missed it. What are you going to do next?
After the PhD?
Oh, I mean,
after
your next step for the PhD and your next step after the PhD.
So I will try to complete this approach. So now we are planning to put a lot of sensors to scan the cheaters as a ground truth data. But I'm trying to estimate the complete cheetah shape from the depth and image. Yeah, but after the graduation, I plan to go back to Japan. Actually, my wife has her own company and she's starting new business. So yeah, I go to back to Japan and get some postdoc position there.
But will you try and continue this research?
Yes, yeah. I'm very so my ideal situation, once 6 months go to the Kalahari and record data and go back to Japan and do some research. Yeah, that's my ultimate goal.
Do any of your students work with students?
No, I'm trying to currently establish a collaboration.
Yeah.
Any other questions?
I guess I have one question. The data collection pipeline from collecting the data to cleaning it to getting some sort of end product as like a mesh or some sort of other thing you're interested in. It seems that there's a lot of individual sort of data cleaning that you have to do for every time you collect data. Do you have a plan to have some sort of automated data cleaning pipeline?
Oh yes. Yeah, actually a lot of reviewers required me. You need to do replace the automatic methods or something, but I know it's impossible now, at least with the latest methods, existing methods. So for example, yeah, 2D key point detections sometimes easy, but sometimes very difficult, especially one of our uniqueness is that we are using zoom lens camera, but many people use usual camera. So usual camera means a wide field of view. So the camera model quite different actually from the zoom lens. To the zoom lens is very narrow field of view. So we cannot simply apply the existing trained big model to the zoom camera scenes. So yeah, that's one of limit of current automatic method. But yeah, we are trying to automatic as much as possible. So if you have any good idea, yeah, I'm so happy with that.
Wonderful. So
Cool.
thank you so much for a really fascinating talk. Yeah, wonderful. Thank you very much.
Yeah, thanks so much.